I offer this as a course, an entire semester course at IIT Madras. So what we are going to give you is, in a nutshell, what speech audition is all about. What machine learning in audition is all about. I must tell you that speech was perhaps one of the first and foremost to start using machine learning algorithms. And it started way back in 70s and 80s, primarily because speech is something where you can see, when I'd ask you to type on a QWERTY keyboard, you learn the ASDF, LKJ, HJ, or whatever. Horrible way of typing, and it's so unintuitive. The keyboard was designed so that the mechanical typewriters would not jam when people typed fast. But all of us are quite happy to communicate via the keyboard to the computer and do it in, you don't mind finger typing and things like that. But when I ask you to communicate with speech, via speech, you will expect the machine to do a lot of stuff. You'll be talking to the machine and say, hey, can I get some tea on the side? That's a very common thing. So, it's a lot of work for the machine to realize that there's a context switch and come back and say, okay, this is what the person means. In the Indian context, it's even worse because we speak multiple languages. It's very common for us to switch from one tongue to another. The Pepsi first, when it came into the country, the ad was, "Yehi hai right choice." Speech recognition even today cannot handle code switching. This is called code switching, switching from one language to the other. Then again, when I speak back, for example, at home I will be speaking in my mother tongue, Tamil for that matter. But when I get into an argument, it will always be English. I don't know why. But interspersed with Tamil. Okay? The problem is we are unwilling to cooperate with the machine when we have to use speech as a modality. Okay? This was realized way back in the 80s when the first systems from IBM and CMU came about. Okay? So machine learning started use of statistical, we called it statistical pattern recognition. And we said statistical pattern recognition techniques for recognizing speech sounds has its, the first such systems was very, very early. 70s, 1952, there was one, but was not really a machine learning system. Started long back. Another problem is when you want to convey something, I ask you to repeat the same sentence, you will seldom repeat the same sentence. You'll be having the document in front of you. I ask you to read from the document, but you will fill in whatever words you feel like, which you think are more appropriate. This is another serious problem with using speech as an interface. Whereas on the computer, when you're using the keyword, I can't change my username. I can't put my pet name there and hope that it will understand. You'll be very careful about it. But when it comes to speech, this is something that we have found very, very difficult. I'll give you a very simple application which we recently built. We built an application for farmers to get the prices of commodities. I don't know how many of you know, the government publishes the price of commodities at midnight. And although the farmer sells his or her wares to the local, to the Reliance and Heritage and all that, they buy the stuff for a song. So the idea was the farmer can get the prices and perhaps negotiate prices. So it's very interesting. He says, I want the price of, bhindi. And he will say, madam, he will add at the end, thinking that there's a person who's talking at the back end. All these kinds of problems are there. So he's speaking in Hindi, he thinks. And then he thinks at the back end, there is a human being who's sitting. And he will talk as if he or she is talking to a human being. So this is what makes speech recognition difficult. But speech recognition today, I think all of you are aware, it is more or less, to many things are somewhat solved problems, not in the Indian context. And, what I'm going to walk you through is the use of speech technologies using machine learning in a very big way. I'm not going to talk about we've also done a lot of work on music technologies. Again, music, for example, cover song detection. You want to find out, if I composed a song and I tuned it and I sang it, I want to find out if somebody else has borrowed the tune, has copied the tune, and things like that. It's very common in Bollywood. Mozart is borrowed, Beatles are borrowed, anybody is borrowed without copyright information for that matter. So these are things that you can do in music. Indian context, again, it's very difficult. If you're looking at Indian music, whether you take classical, you take folk, you take anything, it's still a unsolved problem, even using machine learning. So let me, okay. So this is kind of, I must tell you, as I said, it's a huge list that I have here. And one of the most popular techniques, speaker recognition, which has gotten into banking applications today. I'll talk about that. And one thing is, there's a general feeling that machine learning means deep learning. That is a big mistake. There's classical machine learning, where we use model-based analysis, and deep learning has gotten traction recently. It's not that neural network models were not there for speech recognition or whatever it may be. Very early, 70s, we had them. The difference is that training the neural network was very expensive. We did not have the GPUs or the power of the CPUs, the amount of RAM. To give you an idea, my first machine learning system where I tried to do classification of what is called CIs was, as I think I mentioned it in the other, 1983 to 86, where 64K of RAM, 8-bit machines is what we worked with. But today, what are we looking at? We're looking at 64-bit machines, and we are looking at 450 GB RAM, 17, 18 terabytes of space is a normal server that one uses for machine learning today. That is where we are, all right? So what I'm going to talk about is, I'm going to talk about in speaker recognition, what is the state of the art. Then I'll talk about speech recognition, what is the state of the art. There's something called hidden, because in speech recognition, you have to do sequence recognition, because I'm reading a book I read, or let me give you another example. The teacher said the student is a fool. The teacher said the student is a fool. The teacher said the student is a fool. The semantics, when you look at natural language understanding of this, totally different. That's because the pauses are at the right places, and there you require sequence information. And even if I speak the same sentence again and again, it's not going to be identical. These are issues. How do you work with this? We use what are called standard techniques, or what are called hidden Markov models. Even today, hidden Markov models, there's a hidden Markov model deep neural network version. And then I'm going to talk about speech synthesis the other way, where you type in text and you expect the systems to speak. These are, again, extremely useful for people who are visually challenged, for that matter, to use the computer. They use the voice feedback to type using the keyboard. Many of them are experts at doing it. And how do we perform speech synthesis? And all this has to be done real time. We'll talk about unit selection synthesis and hidden Markov model based synthesis. And then I'm going to give you a very brief overview of sequence to sequence models for speech recognition synthesis, which is neural networks all the way. And finally, if I have time, I'll go over the spike train inference problem, which is kind of both physiology inspired and signal processing inspired. This is just to give you an idea, especially in the context of brain research, where we do not have, in the context of speech recognition today, something like Google uses 128,000 hours of speech. And even then, the Google Mini or Google Home is a dumb machine if you try it. I have one at home, and every day I'm cursing it, saying, you don't seem to be learning what I really want. Okay? It's trained with huge, huge amounts of data. And the reason why I would like to talk a little bit about this is, in the context of brain research, we do not have enough data. And how do you do machine learning when there's not enough data? Here are some papers which we are, okay, these are the papers that we are using for this course. So one of the things that we are hoping is that when we understand machine learning, when we do machine learning, statistical machine learning, it can help the brain understand better. Why do we call it statistical machine learning? Because we believe that, as Ravindran was saying the other day, machine learning will simply not work if the patterns do not have a stationarity. What do we mean by stationarity? The underlying statistical characteristics of the signal do not change with time. I can understand you speaking the same thing. I can understand Y, Z, whatever it may be, primarily because there is some invariance. The problem is when I speak, I'm speaking through this microphone one day. Another day I'm using a gooseneck microphone on my desktop. Another day I'm using my Bose microphone, and so on. Each one of them with its characteristics. I'm speaking from the airport. I'm speaking from the railway station. I'm speaking from various places. How do I get the system to work despite these variations? And top of it, I do not keep my head like this and speak. I keep moving my head from side to side. Those of you who have worked in any kind of radar or whatever it may be, you know that the direction of arrival of the signal has changed. And because of which, there's going to be path difference. Okay? These are issues that we have, and how to be, the idea is that with machine learning, it can help us do all these things better. And even today, I will still argue that despite the Siris, the Cortanas, the Google Homes, and Alexas, still humans are much better at recognizing what a person wants. Okay? So when you compare what is the relevance of speech to this workshop, speech and brain signals, both of them are temporal data which can be described as a sequence of observations. Both are noisy owing to high dimensionality measurements. The other day I talked about EEG signals. We're talking about 128 channel EEG data, so the dimension is very high. Non-stationarity, what do we mean by non-stationarity? First and second order statistics might change with time. Okay? The mean and the covariance matrix of the signal can vary with time. There are several domain dependent factors, like I already talked about channels and so on and so forth. When you're looking at the brain, for example, we already talked about the microphone being placed on the head, and the location of the microphone can change every time you make a recording. Machine learning is extensively used in speech today. We have a number of practical systems, Google Voice, Siri, Cortana, Kindle readers. Here to Read is a new application that has just come up, which will read for Indian languages for the visually challenged, Kindle readers. Okay, so the outline of my talk is primarily going to be on speaker recognition, speech synthesis, speech recognition, and spike train interference. Okay. So what is speaker recognition all about? This is being used by the bank today. Citibank has started using speaker recognition applications. So for example, I can just speak through to my dial number, call it, and speak and ask, hey, what's my balance? Okay? And it'll know that it's your voice, find out what your balance is, and let you know what your balance is. How is this done? And this is just an idea over here. There are two kinds of things in speaker recognition, which we call speaker identification and speaker verification. And speaker identification, for example, you assume that there is a finite set of speakers. You do some front-end processing. You build speaker models, which is what I'm going to talk about. Then you find out you have a speaker, and you find the score. And using the speaker score, you determine what kind of which speaker it is. This is what is called a closed set problem. This is called an open set problem. And why is this important? You have, for example, a PIN number which you type in or something like that. That's called a claim. And then you speak, and then it matches only against your model. This is the more popular model. Why so? Because your PIN can be known to somebody. For example, I know how many of you are aware. When they found out in India, it's very common that ATM frauds happen. People withdraw money from your account using your card and things like that. More often than not, they found that the problem was with people from the family itself. Somebody has your smart card. We keep all our passwords open, including myself. I'll send my daughter and get money from the ATM. Give my card to her. So the idea is, additionally, you use voice, you use fingerprint, and so on. And can you ensure that the money is being given to the right person? Okay. And the two kinds of tasks: text-dependent speaker verification predefined specific password for every user. Problem is there's a little bit of limited vocabulary in a sense, because you have to speak the same password again and again, just like how you type into the computer. Text independent speaker verification, which is a greater challenge, and today used by the banks. No specific utterance, independent of vocabulary, and so on. And how do we go about doing this? How is this done? You build what is called a Gaussian. The original systems were building what are called Gaussian mixture models. For example, all of you are familiar with the Gaussian distributions of a well, have the shape particularly here. Yeah? Problem is, when I speak, depending upon the noise, depending upon the sounds that I speak, the distribution is not going to be a unimodal Gaussian density function. So it becomes what is called a multimodal Gaussian density function. So we represent it by a mixture of Gaussians. Each speaker's data is represented by a mixture of Gaussians, weighted mixture of Gaussians over here. Each Gaussian is represented by a mean, a covariance matrix, and weights. Therefore, the model, for example, it consists of the weights, the means, and the covariance matrix. Fitting, so what happens is we have the speech data from a particular speaker. How do we build a Gaussian mixture model? We do not know the means, nor do we know. We extract a whole lot of feature vectors from the speaker, and we do not know to which of these Gaussians the speaker's feature vectors belong to. Therefore, because we don't know where the means are, it's a chicken and egg problem. So fitting a Gaussian mixture model is what we call an incomplete data problem. Expectation maximization is a technique that is used. You need large amounts of training data to enable this. Today, for speaker recognition, we are able to do with about 8 minutes of data from every speaker. That is a standard benchmark. Still, testing is a problem. It requires at least 30 seconds of data to do pretty good recognition of the voice. And 30 seconds of data is more like a story. You know, you can tell a story in 30 seconds. So it's still not there. What do we want today? We want to bring to give you an idea of what 30 seconds means. An English sentence is normally about 1.5 to 2 seconds long. Okay? Indian language sentences are much longer. They range from 6 seconds to 15 seconds long. Okay? So these are literally stories that you're expecting to speak before my voice can be identified. Okay? So normally what it will do is it will use a shorter utterance to identify. Then it will ask you what your mother's maiden name is, like what your bank has, okay? And go through that too. So it does speech recognition and whatever. So this is the expectation maximization algorithm. Those of you who are doing the course, please realize that because it's an incomplete data problem, because we do not know the mu case, sigma case, and W case, and we do not know where to which of these Gaussians, these feature vectors, xn's are the feature vectors here that belong to, we use what is called an expectation and a maximization phase. It's an ill-posed problem, not a well-posed problem. So we randomly initialize the mu case, sigma case, and W case, and then we find the responsibility of each feature vector being described by the initialized Gaussians. Then once we get the responsibilities, we go through the maximization step. We maximize the probability, maximum likelihood estimation as it's called, re-estimate the parameters. We keep iterating back and forth. So we take these parameters here, plug it back here, re-estimate the parameters, re-estimate the responsibilities, plug it back here, re-estimate the parameters. Keep doing this until the feature vectors have not moved. To some extent, there are issues with this, that the initialization can be quite crucial. So one of the things that we generally advise is that you start with multiple initializations to ensure that your model is actually robust. How do we initialize this? The initialization is essentially done by picking one of the feature vectors, putting it as a mu k, and start with an estimation of the covariance matrix using all the data. Initially, you assume all Gaussians are equiprobable and give 1 over n as the probability of data coming from the Gaussians. Iteratively, it fixes itself. Okay. All right. Then what happened was, the problem with this technique was that it did require huge amounts of data. What do I mean by huge amounts of data is that each speaker's voice used to be represented by about 100 to 200 Gaussians, and you needed large amounts of data for that. Then it was found that it was not very robust. You start with a different initialization, things do not work as well. So what did we do? We built what is called the universal background model, overcomes the huge data requirement for training GMMs for every class. Going back, what we do here is, for every speaker, we build a separate Gaussian mixture model like this. So just imagine each speaker, you're doing about 200 Gaussians, and if you have 1,000 speakers, you need that much amount of data for each speaker for 200 Gaussians to estimate the parameters. To give you an idea what is the dimension of the feature vector, it's a 40-dimensional feature vector. So the covariance matrix is almost 800 parameters. The feature vector dimension, if you talk about 100 mixtures, you have 4,000 parameters. And the weights, which are depending upon 100 weights. So you have a whole lot of parameters to be estimated, and statistics will tell you, whether it's neural network based techniques or whatever it may be, for each parameter to be estimated, you need independent, identically distributed data. A book like Bishop will tell you about 10 samples. Having working in the field, I would say you need 100 feature vectors for every parameter that is estimated. And how many feature vectors do you get per second? You get at most 100 feature vectors per second. So you look at the amount of data that's required for training these GMMs. So what was done was, we said, this is going to be a big problem, so we'll do something differently. So what was done was, we simply pull all the data, build, this blue color is one Gaussian mixture model. It's called a universal background model, which is built for all speakers together. And then we give these speaker-specific data, this orange color data for that matter, and adapt. The mixtures simply move a little bit. You can adapt both the means and the covariance matrices. Notice that these two mixtures have not changed, only these two mixtures have changed, and the orange is the new model for each one of the speakers. The details, the devil is in the details. So what we do is, we at the same time, there is a bit of a problem in the sense that this adaptation, if it does not have enough data, the estimates can be poor. So what we do is, we take a weighted sum of the means of the and covariance matrices of the two models to give the new model for the means and covariance matrices. Normally, we only perform mean adaptation. We do not do covariance matrix adaptation. Although the picture here, for example, that is the blue, the orange will be in the same orientation as the blue and will not change the orientation. Okay. The reason for this is that estimating covariance matrices, for example, if I'm having a 40-dimensional feature vector, you're having about 800 parameters to be estimated. And if I don't have enough data, the model estimation may not be robust. So just moving the means alone is pretty adequate for characterizing each one of the speakers. So what do we do now? We build a universal background model using the blue color. Then we give the specific speakers data and just move the means a little bit. Okay. And during testing, for example, what we do is, we want some normalization that needs to be done. So we test against the claimed model, and then we also subtract the probability with respect to the blue model. Because what you're going to do is, I'm going to estimate the probability when the test vectors come with this orange model and also with the blue model. The difference is going to be used as a threshold to detect whether the claimed speaker is present or not. This is in the context of what is called speaker verification. This is done for every test utterance. Okay? There are scoring. Don't underestimate the need for scoring. People would have talked to you about normalization. It's extremely important. Those of you who are from IIT, you know your grades are relative. So always anything relative to the background model. Okay, that's how the performance of any system is scored. Okay, and to give you an idea, these, when you look at log probabilities, it's of the order of e to the minus 20 and 30, but nevertheless, we can still, I mean, what I'm saying, the range of values is very, very small, but the difference can be large. That is what we look at. Okay, then what happened was, again, although this model is still used, this UBM based model, then it was felt that the problem with this is that these models which we already built, there's still an issue with that, because we are not, see, I'm speaking through the microphone today here, and I'm speaking on the phone, I'm speaking maybe to my desktop computer, one day I'm using your cell phone, one day I'm using my cell phone. All these are different channels. Or I may be speaking through the landline phone. Okay? Now the problem is this model does not take care of these variations in the channel. Okay? So what we did was, we said stack all the, I mean, this is an example of stacking the means. You can stack the covariance matrices and stack the weights. We said, let's say these are the estimated or adapted means, put them together. So this is like taking the data, transforming it non-linearly using the Gaussian mixture models. Then you have this supervector. We call this a supervector, which is the mean of the model. Going back to this picture, I'm going to just talk about the example with the mean, because I'm not changing the covariance matrix. Mean is moved here, mean is moved here, mean is moved here for this orange class. Stack them all together, make a vector. But the problem is, this vector contains information about the speaker and about the channel and the noise. So I need somehow to reduce it to the subspace where only speaker information is available, and that's what we do. So what we do is the following. These are called latent space techniques. There's a technique called principal component analysis. There's something called probabilistic PCA and factor analysis. Those of you who know what principal component analysis is, what do? You take all the feature vectors, then you put it in the, you compute the covariance matrix, find the principal components of the covariance matrix, project along the large variance directions, and take that as your new feature vector. What is it that I'm going to project here? I'm projecting what are called the supervectors. What are the supervectors? The sequence of adapted means, the sequence of adapted covariance matrices, sequence of adapted weights. Okay? So you notice that how is the mean obtained? Using adaptation data, and you've already non-linearly transformed it, because we found the responsibility of the feature vector belonging to a particular cluster as a likelihood. Okay? So that's what we do. Principal component analysis is one, doesn't work too well. And then you had probabilistic PCA, where we said that the noise can be distributed sigma squared I. There's no noise over here. Then factored analysis, where we said we'll have a diagonal covariance matrix psi, and notice that all these and these z's over here are actually the speaker characteristics in principal component analysis, probabilistic PCA, and factored analysis. Notice that everything is normalized now. 0, mean, variance, 1. So we do this transformation. We force it. All right? So to give you an idea of what this is all about, these are the means that I estimated during the adaptation. M is the UBM mean. V is your speaker-dependent components. Then you have the channel-dependent component. And then you have some residual noise component. So what we do is we take these stacked means, and our objective is to find this matrix V. Unfortunately, what do we have? We know what M is, we know what capital M is, we do not know V, we do not know Y, we do not know X, and we do not know. And why does this technique work? Because we believe that, remember that as I said, machine learning is dependent upon structure in the data. If there is structure in the data, there is redundancy. If there is redundancy, then there is some stationarity that is there. When the some stationarity means what? Mean and covariance matrix, weakly stationary we say, are not going to change too much with time. Okay? So that means what? There is, if I take the entire space of sounds, I have bird sound, I have marmoset sound, I have various kinds of sounds, ambulance sound and so on. We believe the speaker subspace is a small subspace. That is the fundamental assumption. And that is fine because there is structure. If there's structure, there is redundancy. If there is redundancy means what? Entropy is small. Entropy is small means, notice that I've traversed various things over here. Linear algebra because I'm projecting, and statistical modeling because I'm using this non-linear Gaussian mixture. V is a set of supervectors over here. Y, these are all supervectors here. V's are the means of the Gaussians, so that means what? This is a space of Gaussian mixture models, and in that space of Gaussian mixture models, there is a subspace which represents the speaker, subspace that represents the noise, and the subspace that represents the channel, and a subspace that represents the residual noise that we have here. This is your UBM, capital M is what is your adapted mean. Again, since we do not have, see, this is like I can do an M minus M over here, estimate V or Y if one of them is known. But none of them is known. So what do? We again use an algorithm which is similar to the expectation maximization algorithm, which means what? I start with a particular assumption of V, estimate the responsibilities of Y coming from that V, initially assume that U and D are 0, re-estimate V, plug this back in, estimate U and X, DZ, and so on. This is called joint factor analysis. Remember that your data, each one of the directions is a set of Gaussian mixture models. Okay? I hope I'm making sense in what I'm telling you. It's not the usual vector space. The vector space after I have transformed it non-linearly using Gaussians. Okay, so it's exactly what we do. You have the speech signal, you have the supervector here, M minus N, and what we're saying is there is, so notice that if I look at this equation over here, I can do an M minus M here, and the right hand side I have these variables which need to be estimated, and what we're saying is if I take, there's a speaker latent space, there's a channel latent space, there is a residual noise space, and our objective is to estimate each one of these. And you will find that this is a very well-known and popular technique that is used in the literature in a very, very big way. It's a very common technique, and I'm not going into the details of this algorithm, but nevertheless, I've put this algorithm over here so that when I share the slides, you have the details of how to estimate these parameters. You estimate the parameters, and finally now, what happens is, finally, what do I get? I can estimate the Y over here. Let me go back to this. And I estimate the Y over here. Y corresponds to the speaker characteristics. It becomes a vector and vector in the Gaussian mixture model space. When a test data comes, I project it along V, get that vector, and I simply have to do what is called a cosine distance match to determine to which class it belongs to. That's what testing is all about. Then this is a fundamental theory behind building speaker recognition models. There are a lot of mathematics to it, and you can go through the details. There are beautiful papers that are there. Then it was found that joint factor analysis, it was very difficult to separate this. So what was done was they came up with a lower dimensional representation which contains only channel and speaker. And then after that, you go through what is called linear discriminant analysis. Those of you who are not familiar with this is again taking those supervectors in the UBM GMM subspace and building one more discriminative model. Again, you have to do normalization. Again, you have to build these discriminative models, and that is the state of the art for speaker recognition. There are used systems using deep learning that have come, but they have again used things from this particular model. You take the super vector, put it into a neural network, and build a discriminative model. One way of doing it. Okay? So a lot of things have come, but still the state-of-the-art systems use this model for speaker verification. I must tell you, this is a IIT Madras too participates. We have these benchmarks every 2 years, and IIT Madras always participates in these benchmarks. There are about 60 teams from across the globe that participate. We are between 30 and 32 in rank, but we are a single system that we submit. There are combined systems that are submitted, and the error rates are very, very small. We have an error rate of about 1%, 2%, which is still not bad because it's better than credit card fraud, for that matter. World over, they have come down to something like 0.05% error. That is, you go and speak to the system, it misses you, 0.05%, or it gives access to someone else at 0.05%, which is much, much better than your Visa card fraud today. Okay? So speaker recognition has come a very long way. But of course, with it comes the other vulnerabilities that are there. We're working on these problems. I can record your voice and play it to the system. This is called spoofing. A big thing today. A lot of work has been done on spoofing. And many of the spoofing techniques, for example, I'm quite proud to state that IIT Madras came up with some feature representation about 20 years ago, 25 years ago. And that feature representation is very good at detecting spoofed signals. So don't think that machine learning will do everything for you. You need to handcraft your recipes very carefully in machine learning. So that's about, in a nutshell, what speaker recognition is all about. Let's look at what speech recognition is. Speech recognition converts, all of you know what your Google and others do, converts a given speech signal into a sequence of sounds, sequence of words. This was the first speech recognition system was in 1952. Basically, the idea is to use the speech recognition to replace the keyboard. It has still not been replaced. I'm sorry, spelling error is still there. But nevertheless, speech recognition systems have become quite good for IVR. For example, I can go to a travel agent and say, I want to book my ticket from Chennai to Delhi on such and such date. I can phone in. Okay? These systems have become very popular today. It's possible. But I must tell you, what it does is, it actually does not try to recognize every word that you've said. What it does is, it will pick up certain keywords. Then it will have at the back end, Google's, the Siris, the Cortanas, the Alexas, have a set of sentences. It reduces the domain. So it knows I'm looking at travel. I'm looking at travel booking, okay, using the keywords. And then it knows what might I want to do. I might cancel my ticket. I might book my ticket. I might change my flight. It knows that. And therefore, it reduces space. If you ask it, if you look at what Alexa or Google do exactly, the sequence of words, it will be almost, 50% wrong. But the keywords would be correct. So using from, to, and so on, we'll pick it up correctly, and that's what is being done. So what did we do? So what is the mathematical formulation for this? We have a set of acoustic vectors, and which we call observations, A over here, and W denotes a word sequence. And what is the difficulty with speech is primarily that the word sequence need not correspond to grammatically correct sentence. In conversational speech, we never ever speak grammatically correct sentences. Okay? So that's the fundamental problem. So we just say, in fact, we never say a speech sentence. We say speech utterance. Because you utter some sequence of words, which perhaps are known to the vocabulary of the system. And what's our objective? To find the best vocabulary of words. So how we do this is, again, a lot of cheating that goes on over here. We kind of hypothesize what word sequence you might have spoken. Okay? Just think, Google has a huge, billions of pages of information that is there. It has organized the whole thing in some kind of a tree, and it simply verifies which is the best word sequence that you might have spoken. Okay? It basically verifies the word sequence. So it hypothesizes a whole lot of word sequences. Then as the acoustics comes along, it drops many parts, realizing, okay, this probability is very low of this guy in the first few frames itself. It'll keep dropping, and finally it will choose the best word sequence. And from that, what it will do is, what does it do now? It converts this word sequence to your search items in the bar where you type in. Instead of typing in, it is recognized and put it there and gives you back the search results. Okay? This is how any of these search engines work today when you use voice for recognition. And so essentially the problem is, I don't try to find out what is the sequence of basic sounds that I have made and then make up the words. It just finds placeholders. This is very much like human beings. When I ask you to read a paragraph, okay, you're not going to read word by word. You're not going to spell word by word. You read very fast, and you essentially suspect you're looking at phrases. Okay? Even more, abstract, the way we look at it. So that's exactly how speech recognition works. It's word sequences that it recognizes. Where have these word sequences been obtained? From spoken data. Do not use much of the text which is there, because they're grammatically correct sentences. We don't speak grammatically correct sentences. Okay? To give you an idea, these things started, early 80s. So from then on, people have been building these vocabularies in a very big way. We call this the language model. The word sequence is called language model. What is the probability of a sequence of words? And what are you doing? What is the probability that these acoustics came from this language model? So let me give you the basics of this. The first set of systems were what are called dynamic time warping based systems. So you have a word over here or a sentence and ideas, because the durations can be different. We call it dynamic time warping because the durations of each one of the sounds between what you have as a reference template and the test template can be different. Let me give you a different example. Suppose I'm recognizing video. This is a common example that I give in my class. I want to identify LBW, leg before wicket. We just won the test series in Australia. And you have different types of bowlers. You have a spinner, you have a fast bowler, and so on. And the problem is, I want one common model for LBW across all of these people. So there'll be something like, bowling action, pitching action, and hitting the pad action. And then what do? You extract the trajectory of the ball, and if it might have ripped off the bails or the stump for that matter, then you give this person out. Right? That's what this whole technique is. Suppose I want to build a machine learning algorithm. What can happen? I'm having a camera which is collecting data at 70 frames per second. Okay? A fast bowler perhaps finishes the entire thing in maybe 30 or 40 frames, whereas a spinner may require 70 frames for the same action. So the durations are variable. A fast bowler has a long run-up. A spinner has a short run-up. Okay? And the turning of the ball matters, the direction in which it turns, especially with the spinner, and so on. And I want to model all of this. Okay? So the time duration that is spent in each one of these actions can be different, and that's why we use a variety of dynamic programming called dynamic time warping, and these were the very, very first speech recognition systems for word recognition, digit recognition, and so on, started a long time ago. Then what happened was, we started realizing we need multiple templates. I need a template for a spinner, I need a template for a fast bowler, medium pace, and so on. Too many templates. Okay? And all these have to be stored in memory. And more the number of templates, the better the systems became. Then it was felt, can we convert them to a sequence of states? Each state has some underlying stationary representation. As I said in the LBW case, I have a bowling action, a pitching action, and a hitting the pad action. There'd be 3 states in my system. Okay? That's how we started. And what do? We make the system learn the characteristics of each one of these states. And it transits from one state to another. Okay? So it remains in the same state or goes to a next state. It can also skip states if you want to. Normally we don't use models with skip, but especially in speech recognition, because we don't want words or sounds to be missed. Okay? So what we have is, put this all together. Oops. So what happens is we have 2 types of HMMs. These are called hidden Markov models. Why are they called hidden? Because the parameters of the states are not known. We do not know which state the data came from. They are Markov because there is a dependence on the previous state. There is a sequence. Okay? You can't give anybody, for example, let's say the bales have been ripped for no reason at all, and it's not part of the LBW, bowling, pitching, and hitting the pad in that sequence, then you cannot give somebody out. So it cannot be taken out of context. So you need the sequence over here, and that's what this is all about. And now what we say is, in each state, I have a set of feature vectors which characterize the state, and each state is characterized by what is called a Gaussian mixture model again, because you can have multiple. Let me give you in the context of speech recognition, we need at least 2 mixtures in every state. Now I suppose many are sleeping. Let me ask you the question, why do you need at least 2 mixtures in every state for speech recognition? At a fundamental level, there are 2 types of characteristics which we need to recognize. Can anybody answer? Speech recognition is purely common sense. I'm asking you a question now. What are the fundamentally 2 different types of voices that we have amongst humans? Male and female. So you need to recognize male and female at the fundamental level. Vocal tracts are different. Child also you can say, but we generally will not give a speech recognition system to a child. Child and female are generally mixed together, which is not correct. The vocal tract lengths of males is about 10 centimeters, females about 14 centimeters. Vocal tract lengths of males is about 17 centimeters. That means the resonant frequencies are different. Sound is produced because vocal tract resonates. Okay? So we need at least at the fundamental level male and female voices, but what happens is when you pass it through various channels, your number of mixtures explodes. Okay? So then what was done was you first started out with we started out with word level HMMs, so it's called connected word recognition, and then afterwards we built what are called context dependent phoneme and oops, I don't know why my student does this. All right. Then we found that you built a separate word model. For each word you had a separate hidden Markov model, and the problem was words which are outside the vocabulary cannot be recognized. Then for each phoneme, each word can be broken down into a sequence of units called phonemes. You built a separate HMM model for each phoneme, and concatenation of these sequence of phone models made up the word. So, and then it was found that because in speech is produced as the output of an inertial system. To give you an idea, what do I mean by inertial system? We're all lazy when the fundamental law of human beings is laziness. We want to do everything with the least amount of effort, including speaking. So for example, I have a sound k, which is spoken where the tongue touches the roof of the mouth at the back. This is a very favorite example of mine. E is a vowel which is in the front of the mouth. Tongue hump is at the front. I want to say key. Then what do? I say, oh, I have to say E next. So I'll put the ka a little bit forward, and E I will move it a little bit backward. Person understands anyway. Okay? So you want to make minimal tongue movements. So what happens is the sound production itself changes based on the context. The E, for example, is affected by the K. The K is affected by the V. It's actually future planning that happens. It's non-causal, actually, speech production. Okay? So what you do is, you say, okay, let me use context before and after, and you build what are called triphone hidden Markov models. We call this problem co-articulation, and again requires huge amounts of data. So we use what are called decision trees. So what we do is, now I build an HMM for, let's say this HMM. I have an HMM for each one of these triphones, a phone in context. So the number of triphones simply explodes. To give you an idea, I have 52 phones in a language. So you're looking at the left context and the right context. So 52 to the power 3, huge number of models to be built. I don't have that much of data. Then what do I say? Okay, some things are sounding similar. I build a common model for all of them. Okay, that's what is done. And hopefully the higher level semantics will take care of things for us. And that's precisely what we do. So we build what is called something like the joint factor analysis. You build what is called a subspace model. It's called a Gaussian subspace Gaussian mixture model. And the characteristics of every state are described by these Gaussian mixtures. So let me just go through the picture of it. What we do is that you have a particular mixture, and it has a particular mean, covariance matrix, and so on. So you see, from here, I adapt for every state. So what happens, just like the UBM GMM that we did in the context of speaker verification, we adapt from the common model to the specific state. Each state is described by a Gaussian mixture model. I adapt from this global model for each state. Immediately what happens is, the good part is the number of parameters that is very similar to joint factor analysis, as is mentioned in the slides over here, and we find that the total number of parameters reduces significantly in terms of estimation. Then what was done was, so we do this a lot of, again here, I'm studying, it is, all of these are chicken and egg problems. You do not know what is the weight, what is to be associated, and so on. So you always use an algorithm like the expectation maximization algorithm to estimate these parameters. Okay. Then what we did was, now it was found that, okay, that's very nice. I have got this common model over here, adapted the parameters of the state, and you'll find, how many of you use Alexa or Google Voice? Okay, only one person. Okay. When you use Google Voice, you must be finding that first time when I speak to it, it comes up with complete nonsense. Then as I go along, the fellow is learning your voice. Fellow or felly is learning your voice, right? So what does it do? You put the speaker characteristics back in. As you go along, you're calling from your phone. It associates, for example, remember it's very clever, okay? It asks you to associate your Gmail address. Why? All of you have done it, right? Google Home if you use. Because it gives you a unique ID. Your email address is a unique identity of you. So then it says, okay, Hema's voice is this. Now let me keep track of her voice. As I go along, I keep adapting. If I'm angry, I mean, it's very interesting to say, oh, I'm sorry, I'm still learning. Please bear with me and all that stuff. Next time, it would have, when I ask the same thing, it's doing a better job because it has learned the characteristics of my voice. Okay, so it adapts to my voice. Okay, so changes the models based on my voice. That's precisely what is done over here. You put the speaker characteristics in, and so, Google has a lot of money and a lot of power. So, as Mriganka said the other day, 100,000 watts, not Mriganka, I think Partha talked about it, 100,000 watts to recognize a sentence, Human being does it in 25 watts. That's a different problem altogether. But well, it's always the power decides what happens. So you do this. Again, there is an expectation maximization algorithm because none of these parameters, all these are ill-posed problems. So you're actually, why am I insisting on this ill-posed problem? Your initialization is very crucial. You can get stuck in local minima. Please realize all these toolkits are available for you online. Dan Povey put his HMMDNN toolkit long back. You try training it without much information. It won't work. It's like Tarla Dalal puts a recipe, and she's not alive, I think. And somebody still runs a restaurant. Still, they know that you'll go to a restaurant and eat. Why? Because if you take the recipe and do it verbatim, even then, you'll never get it right. You'll keep doing it a number of times until finally you'll perfect the salt, you'll perfect the chili, and perfect the whatever. At what time instant should I do the tadka? It's exactly like that in machine learning. People put all their tools and tell you, okay, you can use our tools. It's all free, no doubt about it. But remember that lot of tuning is required. The amount of tuning that is done is simply amazing. I remember Google from, I think last year to this year, 2 years ago, they had a 119-layer neural network. It went to 128 layers. And we don't know what happened in between. What is it? Why did you require the 126 layers? Nobody knows. Okay? And this is every one of these. Because these are ill-posed problems. Ill-posed problems means no unique solution. And you essentially tune it to the particular domain. So what is done is these are replaced by deep neural networks today. And primarily because they can model huge amounts of nonlinearity. These are better classifiers than GMMs. And because we train them discriminatively, it's beginning to get increasingly being used. It's not that neural networks were not there. DNNs were there in, I think, 70s or 80s, first proposed by IBM in Switzerland. Didn't get popular because we didn't have the compute power and new kinds of, and we didn't have these powerful pre-training and optimization techniques. Okay, so now the significant increase in compute power, you have the CPUs and the GPUs, and powerful pre-optimization, pre-training and optimization techniques. Of course, the combination of CPUs, GPUs, your Nirvana chips from Intel have come. It's supposed to take care of it. This is what you do. And for those of you who do not know what a neural network, I think by now you've heard of it so much. You have a set of feature vectors over here. And as you keep on getting deeper and deeper, and one of the things, those of you who might be implementing neural networks, my advice will be to look at the output at each one of these layers for even a simple two-class problem. Try to see what happens. Okay? You will find that what I mean by that is, let us say I have a feature vector corresponding to a particular class I'm training, and the output is either, let's say I'm using a 1 of k representation, class 1 or class 2. Look at what happens at each one of these layers. Then you go through one iteration. Then you come back, represent the data. Again, this is an ill-posed problem because we do not know the weights. Okay? We just have the input data. We know what the output labels are. Look at it at every step, and you will start seeing a separation that comes in. That is, I know I presented data from class 1, so at that point, their output should belong to class 1. I presented the data from class 2, the output should belong to class 2. Just plot it depending upon whatever is the dimension of the data, the sigmoids for that matter, and you will see that as you keep, if your network is well trained, you actually start seeing separation of the classes. Okay, very nicely. And the good part is, if you look at actually it's interesting, what the neural network actually learns is actually Gaussian mixture models. You'll find that it's similar. It has multimodal distributions at the output, at every layer. That's what you see. But what is the drawback of it? It requires huge amounts of data. As Ravindran told the other day, if you have hand-labeled data, use the hand-labeled data with the neural network. It just discriminates a little bit better. That's all. So if I had, in speech recognition, what we do is, we use HMM models first, give that as the alignment. Okay? What do I mean by the alignment? Speech is made up of a sequence of sounds. I don't know what sound occurred. So I have the waveform and the sequence of sounds. Now I don't give it blindly to the neural network. I use the classical machine learning model. It will give me boundaries between the sounds. I'll give it to the neural network, iteratively train it. It becomes a lot better. Okay, that's what we do. And so basically interfacing DNN with HMMs, what we do is the Gaussian mixture model in every state is represented by the DNN, primarily because it's discriminative. You've already heard of this word softmax a number of times. Output of the neural network, you convert it to a probability, plug it back into the HMM-based system, and perform recognition. Okay. So the next thing that I'm going to talk about, I have about 20 minutes of time. The other thing is, let's say I want to synthesize speech corresponding to any text. So that was speech recognition in a nutshell. I want to say hello, good morning. Then there's a speech synthesis system which produces the output or the speech signal. How is this done today? The problem with speech, it's very interesting that, in speech recognition, as long as it gets you where you want, it retrieves the information for you, you're happy with it. In speech synthesis, actually is a much harder problem than speech recognition. Why do I say that? You are unhappy and it will say, I do not understand you. What do you want me to do for you? And it will have absolutely emotionless. Okay? People hate it. Okay? And many times, if you do not train the sounds properly, it can learn completely wrong things. It's a big problem, and we are having this as a very big issue in the Indian context, primarily because even speech synthesis requires huge amount of data for training. And the labels must be extremely accurate. And in India, we have a lot of problem because there's this chalta hai attitude, I said, TK, it's okay, it's more or less correct. The fellow would have said from instead of to. Oh, that's okay. I transcribed it as to instead of from. Only one mistake, no, it's okay. But that means what? Instead for training the model from, it is using the waveform of to. And then when I ask it to speak, instead of saying from, it's going to say to. It's a big problem in speech synthesis that we have. There are two different kinds of techniques. People still rely on what is called unit selection synthesis, where you collect the speech waveforms of these fundamental units in various contexts. And you use what is called a classification and regression tree, again a machine learning model, to find out which waveform to use in which context. Your Siri, Google Voice still use unit selection. They do not use statistical models. All the statistical models are getting popular in the context of the Android-based systems. So you have this huge deep tree. The same sound is available in multiple contexts. You want to plug the emotion back in based on the emotion that is associated with the spoken sentence. Everything is done, and then you put them back. It's again a laborious task. This gives you the various components that are there. You take the text, process the text, and then put in the prosody, because I don't want to be, don't want to look indifferent to the subject over here. When you generate the pronunciation, put it back. There's something called source information that is there, because the way we produce speech, and then normally use what is called a multilingual database, because we're looking at code switching, because I wanted to speak in multilinguality. I want the system to say, "Ehi hai right choice." Okay? And this has become a very popular technique today, popular, and is being used quite extensively. This is what your machines have today. Your Siris and your Cortanas use what is called unit selection. What is done today is, let me skip this, unit selection is simply storing templates of the waveforms. Use machine learning to find out what is the best context when you split the text into different subword units, and plug those waveforms, concatenate them, play them back. This is still the best today. And when you connect waveforms, for example, you take care of the boundaries and so on. But the problem is, again, the footprint is very large. To give you an idea, we store something like, almost 700 GB of data for giving you good speech synthesis outputs. Again, diving deep down the tree, you need GPUs, you need CPUs to find out which is the best set of waveforms to pick up. So today, for example, new thing called, just as the hidden Markov model was used for recognition, it can also be used for synthesis. It's what is called a generative model. Take the speech database, you build HMMs, then you do text analysis, produce the feature vectors, produce speech. Fundamental issue with this is that duration modeling is a hard problem. Recognizing what a sound is. Did you say same or did you say same? Do you want to say, it's the same thing that I want you to do? Or it's the same thing that I want you to do? These are two different things. So the duration of the A in same was different when I spoke, for example. How do you fix all this? A lot of work on machine learning for this. This is the standard model that is used, what is called a source system model. The vocal folds vibrate, producing the source. It's like music, you strum the guitar, right? You keep your finger in one place, you pluck the guitar. The plucking of the guitar also will decide the quality of the sound, and the location in which you place your fingers on the guitar will also produce an appropriate sound. This is how speech is produced. The whole vocal cords are primarily like an acoustic tube, and everything is done using a mathematical model like this. We called it, because we keep changing the sounds, we use a different type of filter every time for different sounds that are produced. Okay, and a lot of work you put in phonetic, linguistic, prosodic, and sequence of steps in it, do the text processing. Again, once you process the text, you have subword HMMs, each of the fundamental units, generate the observation sequence using the system model, generate the source using the source model, and produce a speech. Okay, and again, then afterwards synthesis, you have what is called the MLSA filters and the straight filters, which will produce the speech output appropriately. To just show you what we actually do is the following. In synthesis, I know what I have the models which I've already built. I have the word sequence which I want to generate, and then what it does is generates the observation sequence for you, and once the observation sequence is generated, I can produce the speech output. Okay, so you have the model parameters, training data, transcriptions, synthesized speech output, input, text is what we do. And here is a pictorial view. What is done is you take the entire sentence, because in speech synthesis, we do not process phrase by phrase or word by word or whatever. We produce the entire sentence together because I want the prosodic characteristics, the emotion associated with the entire sentence. And that's what this left guy is. What is the set of feature vectors? Again, speech synthesis is an ill-posed problem. We do not know W, we do not know C, so we iteratively keep re-estimating the parameters until you're satisfied to some particular level and you plug it back in. Okay? So I'm not going to talk about this. Let me skip this because I have another 10 minutes. And today, what is the state of the art? Sequence to sequence models take a lot of time to synthesize or recognize speech, but I would be remiss if I don't talk to you about it. It's used for both automatic speech recognition and text-to-speech. I'm just giving you a picture over here. In automatic speech recognition, we give the feature vectors and produce the text output. And what is used? We use what are called bidirectional long short-term memory. And I'll just tell you what it is in a little while. Basically, these are special types of neural networks that are used to model the context. Because I said, in speech, for example, I plan before I speak. So this becomes a non-causal system. That's why I need bidirectionality. Okay? Talk about this in a little while. Many layers. The layers actually start becoming more and more specific. So basically, we call the sequence-to-sequence models because I give a sequence of feature vectors and out comes a character or a sound sequence. Okay? TTS, on the other hand, just the other way around. I give the sequence of characters and then I produce the sequence of feature vectors. All right, so it's just the reverse problem. You can almost use similar models for both of them. And basically, let me give you the most popular models in deep learning for sequence recognition are what are called recurrent neural networks, where the output is fed back to the input, because the current output has an effect on the current output is dependent upon the previous output, or is dependent upon the previous output. That means as a current input feature vector, along with that, let me go back to this. So what I do over here is I take the output here, put it back in. I can, if I have very deep layers, I can decide where I want to put it back in. Okay? Because depending upon how much context I wanted to learn, and that is what is a recurrent neural network. And we've done a little bit, I'll tell you what we have done in the context of this long short-term memory, because we want to, So if you look at short-term memory, stars are in the sky. Lucknow is my neatest place. I go through a whole lot of things. And finally, I say speak Hindi. That means what? I'm associating here Lucknow with the language Hindi. This is called long-term memory. Short-term, stars and sky, and then in a single sentence. I don't do more than that. So what happens is, the drawbacks of recurrent neural networks is they cannot handle this, and that's why you use long short-term memories. And this is just a pictorial view. This is a recurrent neural network. It's like a tan H, one single function that you have. Here, on the other hand, a long short-term memory, we have what is called an input gate, a forget gate, and an output gate. So basically, a forget gate will say, hey, this is, I'm totally changing the paragraph. So don't learn any information. Don't keep the past. Forget the past. Okay? And input gate, when you want to give it in, decides what information should be retained for the future, what information needs to be output. So this is what a long short-term memory unit looks like. And what happens? You have a stack of these. And then you say not unidirectional. I want to do bidirectional. So I'm going forward. I'm also going backward on the long short-term memory, because speech is non-causal. And then not only that, you're not satisfied with this even. You say at every time instant, I want a stack of these guys. So I do 3-dimensional LSTMs. It's just not, this, let's say at one particular time instant, I'm going to say put a whole lot of guys at the back, because so much context that is there. Okay? This is what the state of the art is. And and these models are what we also call encoder-decoder model. Encodes the speech information, out comes the speech information. There are such models here. There are ways of training it. I must tell you, it's completely non-trivial to train these models. What I mean is, you need to know the domain quite a bit. All these code is available on the web, freely available on the web. But training these systems requires huge amounts of data. And the state of the art today is the bidirectional LSTM model. And you have something like 126 layers of this. So LSTM 1, 2, 3, whatever. And remember that this is there for every input that you have. Normally, you choose about 15 into 40, okay, 600 dimensional input vector to the system. And it really requires huge amounts of data. So what, again, of course, during training, you need labels. So what they do is they take it from the conventional machine learning algorithms, plug in the labels that you get, and then the neural network is a little easier to train. Still, you need huge amounts of data to do this job for you. And in addition to that, there's something called an attention that has come in. Basically, you can decide what you want to attend to. And again, I mean, you may think, who is going to tell what the attention is? Everything is automatically learned from the data. But I must tell you, initially when you try it, although all these theories will tell you this, it's simply not trivial to learn. You need some initialization. As I said, all these are ill-posed problems, right? So you need some initialization. You iteratively re-estimate. So it's like, I always say, if you want to solve for a nonlinear equation, what do? You find a region where you expect the solution, and then you kind of focus towards the solution, the fixed point theorem. Okay? So in much the same way, whether it's neural networks, classical machine learning, what have you, you need these initializations which are done very, very well. Okay? So maybe I will stop here. I won't talk about spike-train interference because I already, you have done this in the context of brain. Here is an example where, to give you an idea, what is done is data is collected simultaneously from the mouse brain and also my calcium fluorescence signals. Mriganka will talk to you about it. And objective is to find locations of these spikes because, as he said, it's like pulse position modulation. Idea is to find where these spikes occur, and that's a hard problem. But unfortunately, we do not have tons of data like in speech recognition to train these models. So what we did was we developed some, so this is exactly what a mouse is looking at a picture over here, and this neuron is firing, and our objective is to capture the low time instant at which this firing happens. So there is something called calcium imaging that is done, electrophysiology where they put the microphone at the place on the neuron. Calcium imaging is kind of somewhat passive in the sense that they put a glass window on top of the head of the mouse and then see which neurons fire and collect it. And our objective is to find when these neurons are fired. And I must tell you, we started with deep learning models. It simply did not scale. This is just to give you an example of where we found good signal processing actually work. Those of you who are in electrical engineering, we found that this is what a calcium signal looks like, and this is the predicted pulse train, and this is the ground truth as obtained from the microphones. And we found that this works well. And now when you take this and plug it into the machine learning algorithms, we get even better results. Here are some details to just give you an idea. So to summarize, I have 5 minutes. At least I need to give you 5 minutes for questions. We've used machine learning techniques to address different types of problems in speech processing and latent space techniques such as joint factor analysis and SGMM. Joint factor analysis for speaker verification, SGMM for speech recognition, and nonlinear and discriminative training of DNNs. The HMM DNN systems have become state-of-the-art. HMM-based speech synthesis, still unit selection synthesis is the state-of-the-art, but HMM-based synthesis enables small footprint. The quality is not very good, and we've looked at signal processing and machine learning for spike influence. The trend today is sequence-to-sequence mapping, waveform to words to waveform. Big problem is that one of the questions that we're asking is, as I said, the biggest problem for all of us when you're looking at labeled data. For English, for example, people have been collecting labeled data for 40 years now. When I come to Indian languages, the digital resources are very small. So one of the questions that we are asking is, do you really need textual representations at all? Does the brain actually store textual representations? What is the, it's believed that the brain stores messages. What is a message? We still don't have answers for that. Thank you very much.